I want to give an overview of sort of this field of algorithmic fairness today and what we've been working on, what I've been working on for the past year or so. And that's mainly concerned with one type of fairness metrics, that is group fairness metrics, and I'll explain what they are in a bit, and how we can use them in practice. So hopefully this will be interesting for both people who are interested in the theoretical side, but also in the practical side of how we can actually apply this. And so this is the outline for today. So we'll first start with an introduction to fairness and ADMs. ADM is short for automated decision making. And again, I'll talk about what that is exactly in a bit. And then we'll look at how fairness is relevant in the context of automated decision making. And then in the second bigger part of the talk, we'll look at group fairness metrics. And so, as I said, group fairness metrics are a specific type of fairness metrics, a specific way of measuring fairness. And so I'll first give an overview of these different categories of fairness metrics, but I'll keep it brief because then we'll do a deep dive into group fairness metrics and the questions that you may have when you're trying to apply them in practice. And so some of these questions are, for example, how do I make a choice between fairness metrics? How do I use them to ensure greater fairness? What's the lawfulness of approaches like these? Because oftentimes we have to collect sensitive data or privilege one group over another, and it might seem unlawful to do these things. Then we'll look at how we can balance different optimization goals. And finally, I'll briefly talk about the role and the limitations of using such metrics. And then I'll introduce our team briefly and the projects that we work on, and then we'll have some time for questions and answers. So yeah, let's get started with the first point, ADMs and fairness. So ADM, as I said, is short for automated decision making. In the title of the talk, if we go back, I was talking about algorithms, but that's just a shorthand for like automated decision making. That would be the more precise term. We just use algorithms because it's broadly understood in some form. But we're usually talking about automated decision making. So that means we're looking at decisions that are either fully or partially automated through some sort of algorithm or machine learning model. And of course, we're particularly interested in fairness when it's influencing people's lives. And this happens more and more. So questions like the ones you see here are more and more decided through automated decision making. So this could be whose credit loan application is approved. That's highly influential, right? Whether I can buy this house or build a house is important in my life. Who's admitted to university? This is a high stakes decision because of course I want to be admitted to a good university to get a good job, etc. Who's invited for a job interview? Whose application for social benefits is approved? Who is investigated for social benefit fraud, on the other hand? Whose family is investigated over child protection concerns? And all these questions are obviously super important in our lives, and we want them to be made well. But they're more and more being automated, and there are examples of this around the world, not just in the US, but also very much in Europe and lots of European countries. And so this is something important to look into. And so the example that we'll use in the talk is, I'll try to sort of work with one example, and it is credit lending. And the idea here is that we have a person who applies for a loan at a bank, sends them their data. This is what the bank then considers the input data, feeds into their model, and the model gives them a prediction, usually on a scale of 0 to 1, of how likely they are to repay the loan. And then the bank makes a decision based on that prediction from the model, and that is they either give the person a loan or they deny them the loan. And this could then either be made by a human or by a simple algorithm that looks at the threshold, for example, and says everyone with a score of above 0.8 simply gets a loan. So that's a very straightforward example. And of course, here, again, it's important that we make the right decisions because these are important decisions that are influencing human lives. But you may ask what's so special about ADMs, because of course, this has always been an important decision, even when humans are making it. That's no different now. But what's different now is that when we have the data that's being fed to a model, we can make a lot more decisions because we can make them a lot faster. We don't have to have humans who look through tons of documents, but we can simply feed the model a lot of data, and within milliseconds, we get our prediction and our decision. And so this raises questions of transparency, interpretability, fairness, and all these things. So if a bank clerk, for example, disagrees with the decision by the model, can they actually understand why the model makes a different decision? Is there some sort of way to figure out what part of the data exactly led the model to make this decision? And maybe then the bank clerk can sort of see why this happens and can see some hidden patterns that they didn't realize were there earlier, or is it just a black box and they sort of have to trust it or not trust it, however they feel like. And then also the question of fairness is obviously important, and what we're interested in today is the model fair to women, to different marginalized groups, what's happening at that level. And yeah, of course, we're focusing on fairness today with good reason, because in recent years, you've probably seen all these headlines about algorithms or machine learning or ADMs, however it's called, however you want to call it, being racist or sexist or ableist and all these things. And so you might wonder, why this is even happening in the first place? Because shouldn't ADM systems be better at making decisions than humans? Shouldn't they be more precise? And shouldn't they then maybe be more fair or more neutral or something like that? But of course, ADMs will only do what you ask them to do. So if you optimize a machine learning model to maximize the accuracy of predictions or the utility of the decision maker, that's exactly what they'll do. But they won't look at fairness. Fairness is another aspect that might be different from utility in some situations. And if you don't take fairness into account in the model design process, of course, it won't be part of the results that you get. And so, yeah, fairness has to be taken into consideration when designing these models. But then the big question is, what even is fairness? How do we design for fairness? And so we're going to look at a simplified setting today, because that just makes explaining it a lot easier. We're going to sort of look at a binary setting where we assume that ADMs distribute something, and that is usually either a benefit or a harm, something that you want or don't want. So in the case of university admissions, we look at who's admitted to university. That's usually a benefit that people want. In the case of social benefit fraud investigation, that's usually something people don't want. But we're looking at something quite binary here. And then we are asking if the distribution is fair. So for credit loans, it's something that people want. We're looking at whether the distribution of credits is fair. And so what we use for this is two variables, y and d. We use y to denote our binary current truth that we have in the database. So we assume we have a database full of people who either repaid their loan or didn't repay their loan. And then we feed this database into our model to test it, and we get a decision for each person from our model, and that is either the loan is approved or the loan is not approved. Now let's assume that we have 8 people in our database. You can imagine 80,000 people or something like that. But for simplicity, we'll just use 8 people. And we have 4 on each side. Can you actually see my mouse? That would maybe be helpful. Yeah, okay, awesome, thank you. So we have 4 people on each side. We have 4 people who repay their loan and 4 people who don't. And now let's assume we have 2 different models, both with the same accuracy. So on a superficial level, it might seem as if it doesn't really matter which one we pick, because both are equally accurate. But let's see what they actually look like, what outcomes they produce. So in this first model, out of the 4 people who repay their loan, 4 of them actually get a positive decision. So they actually get a loan. So that's great. And then out of the 4 people who don't repay their loan, 2 are correctly denied a loan, but 2 are incorrectly given a loan. So that's how we get to the 75% accuracy. And then in the second model, basically the opposite happens. Out of the 4 people who don't repay their loan, 4 of them are correctly denied a loan, but out of the 4 people who repay their loan, 2 of them would be denied a loan. And so even though we have the same accuracy for both models, I might think it doesn't really matter which one we choose, because they're equally accurate, and that's all we care for. When we look at the fairness, it actually does matter which one we pick, because arguably model 2 is unfair for those who deserve a loan, because if we look back at those who deserve a loan, so those who repay their loan or those that we assume deserve a loan, then only 2 of them actually receive a loan, so only 50% of them, which is arguably unfair. And then now let's assume that we actually, instead of just having blue squares here, we have two salient groups. And you can imagine these two groups being based on gender or race, religious beliefs, sexual orientation, etc. And we just assume that we have two groups here. That's of course simplifying the word a lot. Usually we'd have more groups. So you can, for example, imagine men and women, but that's still simplifying, of course. And it's much more complicated in practice. But for simplicity's sake, we'll just stick with two groups, the blue squares and the yellow rectangles. And we assume that we feed the data from both groups into the same model, but group 1 basically receives the outcome of what model 1 produced, and group 2 receives what the model 2 produced. And so again, we have 4 people on each side in each group, 4 repeated alone, 4 don't repeat alone. But now the outcomes that we get from the model is, as I said, the blue group receives the outcomes from model 1, the yellow group receives the outcomes from model 2. And now the question is this distribution fair? And how would we measure that? So for that, we can first look at the accuracy. So maybe we'd say if the accuracy is equal, then the model is sufficiently fair. And so in this case, we see that, of course, both models have the same accuracy. So maybe some would say this model is fair, it's fine. What else could we do? We could look at the acceptance rates of both groups. And here we see that 6 out of 8 squares are accepted, but only 2 of the triangles are accepted. And here you could say that's unfair because these rates are unequal and they should be equal. We could also look at the true positive rate. So for the true positive rate, what we do is that we look at all the people who repaid their loans, so all the people on the left side, and we look at how many of them were actually given a loan. And so for the blue group, that's 4 out of 4, that's 100%. For the yellow group, it's only 50%. And so here you could say the chances of people who deserve to get a loan, of them actually getting a loan, are unequal. And that's unfair, maybe. You could also look at the false positive rate. So that's looking at all the people who don't repay their loan and checking how many of them are incorrectly given a loan. For the blue group, that's 2 out of 4. For the yellow group, it's 0 out of 4. And again, we have this disparity in these false positive rates that you might say that's unfair. So we just saw a bunch of different ways of measuring fairness, and that's just a small snippet of how many fairness metrics there are. And the question now is, which one should I choose in practice? How can we actually evaluate fairness? Should everyone have the same chance of being accepted? Should everyone who deserves a loan have the same chance of being accepted? And there are different ways of looking at this. And there is no clear answer, and it's very much context dependent how you measure fairness. And that is why we have so many different ways of evaluating fairness and dozens of fairness metrics in the literature. And so in the second part, I want to look into group fairness metrics. So again, I'll sort of introduce the categories of fairness metrics that we have in the literature, and then do a deep dive into some of them into group fairness metrics. And just FYI, the metrics that we were just looking at, equal, true positive rates, etc., those were group fairness metrics. But yeah, so generally in the literature, you'll find 3 broad categories of fairness metrics, of ways to measure fairness and evaluate fairness. The first one is group fairness. That's what we just looked at. That's where you take different salient groups, 2 or more groups, and you compare them with respect to some metrics. So this could be the true positive rate of the group. This could be the acceptance rates of the groups that you compare, things like that. And then you're trying to equalize them. Another way of measuring fairness are individual fairness metrics, where you demand that quote unquote similar individuals receive similar outcomes. So if you think that 2 people are sort of similar, they should receive the same outcome. And then there are causal definitions of fairness, which allow us to ask what if questions, such as what if I was born as a man instead of a woman, would I have received a different outcome? And so what's sort of special about individual fairness is, and causal definitions of fairness, is that for both you first need to make some definitions. You sort of have to define stuff first before you can measure stuff. So for individual fairness, we're looking at similar individuals receiving similar outcomes. So for that, we need to define what similarity means in the context of our application. for causal definitions of fairness, we first have to draw a causal graph like that before we can start measuring stuff. And so both of them require a deep understanding of the context of the problem domain that we're in before we can start measuring anything. And group fairness is kind of different in that way, because for group fairness, all we need is the outcomes from the model and the sensitive attributes of the people that we're looking at. So we need to know their gender, their race, religious beliefs, or something like that to measure these metrics for different groups. But as long as we have that, we can immediately start measuring stuff. So as we just saw with that circle, we can easily measure the true positive rates of the groups as long as we have the model outputs and the sensitive groups. And these metrics are very easy to implement. They're already implemented in a bunch of tools. So it seems like you could just start using them. And it seems like maybe they're probably super easy to use in practice because they're already implemented. We can just start using them. But that's of course not the case, because I already talked about this choice problem. How do we actually make a choice between different fairness metrics? Because we know from the literature that these group fairness metrics, or the three biggest types of group fairness metrics, are not fully compatible. So we can't fully fulfill all of them at the same time, or even two of them at the same time. So we have to make a choice between fairness metrics. Then there's the question of maybe we can partially fulfill them to some extent, try to fulfill two of them a bit at the same time without fully fulfilling them. There's the question of what do we do if we want to balance fairness with other optimization goals? How lawful are these approaches? And what are the limitations of these fairness metrics? And so we can see that group fairness metrics still require a deep understanding of the problem domain, just like individual fairness and causal definitions of fairness do. So they might seem easier to use in practice because you can just start using them, but you really have to think about which one you're using. And there are a lot of unanswered questions before we can use them. So what do we do now? So the goal of our work, or our project, is to enable stakeholders to have meaningful discussions about group fairness metrics and to build less discriminatory ML models. So we're basically trying to help people to understand these fairness metrics, because they can be quite tricky to understand, and to have discussions about them and the ethics of them. So in what context does this fairness metric make sense? In what context does this one make sense? What's appropriate for my context, so that people can actually build less discriminatory machine learning models. And so the first aspect here, arguably the most important one maybe, is this choice problem. Because again, we can't fulfill all fairness metrics perfectly at the same time. So we have to make a choice between them. When we've built a model and we're trying to evaluate it, it doesn't really make sense to look at all fairness metrics, because we already know we can't perfectly fulfill all of them. So we have to think about which one is appropriate for our context, and then try to evaluate this one and see if we're doing well. And so I briefly want to give an overview of the three types of fairness metrics, of group fairness metrics, that we're typically looking at based on this Fairness in Machine Learning book. I'll try to sort of keep this brief, but just so that you get an idea of what these fairness metrics are. But if you don't fully understand them, no worries. And you can always ask questions about them, of course. So the first one is independence. Independence demands that the decisions D are independent from the sensitive attribute A. So what does that mean? That means that if you're looking, that means that the probability of getting a positive decision, so of getting a credit loan, let's say, is equal across groups. So that men and women should, for example, have equal acceptance rates. Separation demands that the decisions C are independent of the sensitive attribute A, given the ground truth Y. So if you were looking at people with the same ground truth Y, so if we're looking at all the people who repay their loan, or at all the people who don't repay their loan, then the probability that they get a positive decision should again be independent of their gender, for example. So the chances of women and men getting a loan should be the same if we're looking at the people who actually repay a loan, and the same for the people who don't repay their loan. And then for the sufficiency, we demand that the ground truth Y is independent of the sensitive attribute A given the decisions D, meaning that if we look at all the people who receive a positive decision or receive a negative decision, so all the people who get a credit loan or who don't get a credit loan, then the repayment rates should be equal across groups. So if we look at all the men and women who receive a loan, the repayment rates of men and women should be equal. And if we look at all the people who weren't given a loan, then the share of people who would have repaid it should still be the same. So that translates to equal positive predictive values and equal false emissions rates if you're familiar with confusion matrices and all the stuff you can calculate from them, but if not, no worries. But the important thing here is that in this binary setting that we're in with a binary ground truth, a binary sensitive attribute, we know that we can't fully fulfill two of these metrics at the same time. So what we looked at in a recent paper was we were trying to partially fulfill two of them at the same time. And we found that independence and separation are gradually compatible. So they go sort of hand in hand up to some degree, not fully. We can't fully fulfill both of them at the same time, but they're partially compatible. But with separation and sufficiency, we didn't find any signs of them being compatible. So it seems like we really have to make a choice between those. They seem to be quite, they are opposing each other. And so the important question to answer now is which fairness metric is appropriate in my context. If it's independence, if I find that maybe it's independence and another group says it's separation, maybe we can try to fulfill both of them at the same time. But if one group says it's separation and another group says it's sufficiency, then that's sort of an issue because then they're not really compatible and we sort of have to make a choice. So to think about which fairness metric is appropriate, this is a really nice framework from Friedler et al. From their paper on the impossibility of fairness that we extended in a paper that we published this year, and I'll talk about the extension in a bit. But to sort of introduce you to the framework first, I like using the university admissions example, which is that students are admitted to university based on their grades and standardized test scores. And so the framework that they came up with consists of three spaces. Let's start with the decision space. The decision space is the space of decisions, as the name suggests. So in this case, it's the admission decision. And these decisions are based on the observed space. So in this case, the university makes the decision of who to admit to university based on the students' grades and standardized test scores. But of course, that's not what they actually want to base their decision on. They probably want to admit students with good math skills, good language skills, and they're just using the grades and standardized test scores as a proxy. And so the math skills and language skills are in the construct space. That's sort of an abstract space that we can't actually measure. It exists. Students have math skills, students have language skills, but we can't actually measure them. So we take measurements of it, but those are just proxies in the observed space. And so these representations could be quite noisy. And so there could be measurement bias. So let's assume that for one group, for example, the tests are really bad at measuring their math skills. And in that case, the observed space is just a very noisy representation of the construct space. And this could lead to issues. So if we assume that we have two groups and they're equal in the construct space, so they have the same math skills, the same language skills, but because of this measurement bias, because the test doesn't work well for the blue group, the orange group appears much more skilled than the blue group, and they're admitted to university at a higher rate. And this is a case where independence would seem intuitively unfair. So again, independence demands that we have equal acceptance rates between groups. And here this would be violated because the orange group is accepted at a higher rate, but it seems intuitively unfair because they're actually equal in their skill set. So this is one way of thinking about when we should pick independence. So here it might make sense to actually enforce independence to sort of correct for this measurement bias. And then we extended this framework to add another space, and that is the potential space, which is basically the innate potential of the people. So their innate ability to be good at math, to be good at languages, etc. And this is then developed into the realized abilities that we care about at the time that we're making the decisions. But again, there could be some sort of bias here that we call life's bias. So let's assume that if we're comparing, for example, low and high income families can probably afford private schools, tutoring for their kids. They have better access to education, etc. And so even though the two groups might be equal in their potential on average, one group will have higher math skills, higher language skills in the construct space at the time of decision making. And so here's another case where we could say, oh, this bias here that we have in between the spaces is unjust and maybe something that we want to correct for, because maybe the goal of the university isn't to admit the students with the best skills at the moment, but those with the highest potential, and those that can actually develop the same skills or better skills as long as they're given a chance. So we might think that we should correct for measurement bias or unjust lives bias through enforcing a metric such as independence. And so when we're thinking about the choice between different fairness metrics, what we can do, or what we should do, is that we should think about what justifies different decisions. So what justifies differences in decision space? Based on what grounds do we deny students admission, and based on what grounds do we admit them to university? And then another crucial aspect is to think about the consequences of those decisions. So what happens if we admit those students to university? Will this reduce inequalities in society? Will this reduce injustices? And so that's just a brief overview of how we can think about inequalities and injustices, which then helps us to choose between fairness metrics. And of course, this is no question that we can answer with math or computer science. It requires a deep understanding of the domain, because we have to sort of figure out how biased these tests are, for example. And you can do that experimentally, but that's probably more of a job for a sociologist, for example, than for computer scientists alone. And so when we've sort of figured out, when we've settled on a fairness metric, let's say we think separation is appropriate for our case, and we realize that our model doesn't actually fulfill separation, what can we do now? So there are basically two options, what Ben Green refers to as the substantive approach and the formal approach. The substantive one looks at deeper reforms. So it tries to address the root cause of the problem. So this could be school reforms, this could be providing better jobs for families in neighborhoods, etc. Basically, yeah, addressing the root cause. And then the second step is oftentimes easier to implement and is much more technical. That is implementing formal improvements. So basically adjusting the model so that it fulfills the fairness metric that you're trying to fulfill. So if your model doesn't fulfill separation, you can tweak the model so that it actually fulfills separation. And there are different ways of doing that. So if you look at the training of your model, you basically have three phases. You can start before you start training the model by adjusting the data, for example, by putting more examples in of the marginalized group repaying their loan. You can also intervene during the training of the model by not just optimizing for profits or utility, but by actually making fairness a constraint. And then the third step is what we'll look into more in this talk, and that's when the model gives you your predictions, you can apply group-specific thresholds to adjust these different group fairness metrics. So usually what we do is we use a single threshold, but you can use group-specific thresholds. So here is sort of an illustration of that, where in orange, we have the scores that the model gives to men. That's supposed to tell us how likely these men are to repay their loan. And then in blue, we have the scores of the women, how likely the women are to repay their loan. And the scores of men here are generally higher than those of women. Oh, and then in the shaded areas, we have the men/women who are actually repaying their loan. And so if we apply a single threshold here, we can see that out of the shaded orange area, so out of the men who repay their loan, let's say 95% of them get a loan. But out of the shaded blue area, so out of all the women who repay their loan, only 40 to 50% get a loan. And if you think that is unfair, then what you can do is you can just apply two thresholds. So you can use a threshold for men and one for women. And here we can now see that out of the men who repay their loan, so again, the shaded orange area, 80% of them get a loan. And for the shaded blue area, again, everyone above the threshold gets a loan. Sorry, I forgot to mention that. Out of the shaded blue area, 80% of them are above the threshold and receive a loan now. And so now we actually equalize the true positive rates by using two separate thresholds. You might feel uneasy about that. Maybe that's, maybe you're not comfortable with using different thresholds for different groups. And you may question the legalness of this approach. And so that's what we looked at in a paper with two legal scholars, where we looked at this metric at equal true positive rates, which is also known as equality of opportunity in the literature, and that demands that every person who would pay back their loan and would thus deserve to be given a loan has the same probability of obtaining the loan. And the relevant laws that we looked at here are anti-discrimination law, because of course we're doing it to increase fairness, and data protection law, because what you need to implement that approach is for every person, you need to know their gender, which could be critical. And so what we found is that these different thresholds would be seen as a form of positive action or affirmative action. And so it's legal as long as it has a reasonable justification and pursues a legitimate aim. And in this case, the legitimate aim is increasing fairness for women. But this comes with a proportionality requirement that tells us that the impact on the group with the now higher thresholds, so for men in this case, has to be proportional. So if the threshold was like super high and would be impossible for men to get a loan, this would likely not be legal, but as long as it's proportionate, it seems likely that this is permissible under EU law as a positive action. But there is no case law yet, as far as I know, that would actually agree with this, but this is our finding that it's at least likely permissible. But then an important finding here was that we still have to balance the interests at hand. So we have this sort of proportionality requirement, and we do have to balance the different interests, such as the data protection of the individuals and their sensitive attributes. We have to balance it with the economic costs for the bank, for example, who of course still want to minimize the amount of incorrectly given out loans. And the other main interest for us is increasing fairness. And so when we're trying to balance different goals, the question is, how do we actually do this? How do we balance out different goals? And so that's, of course, as I said, not what's usually done. Usually companies just go for the highest utility or the highest profits, but it is often harmful for fairness. It comes with a cost for fairness. And what we could do is to sort of try to balance out these goals. And so one way of doing this is using some sort of Pareto front, where you plot utility against fairness. And both are in quotation marks, because of course you first need to define utility, and you first need to define fairness by picking a certain fairness metric, for example. And what companies usually do is they would go for, so these crosses are basically, could be different models or different threshold combinations that then give us different utilities and fairness values. And so picking this option would be a bad idea, because we can easily improve utility while also increasing fairness. So we're going for high fairness, high utility. So these options would all be pretty bad. But what companies would usually pick is this one, because it has the highest utility. But of course, we can see that we can easily improve fairness while only losing little in utility. So this might also be a valid option. In other cases, it might be a reasonable choice to pick the one with the highest fairness, because maybe fairness is super important in that context, and losing that much in utility is totally acceptable because fairness is such a main concern. On the other hand, maybe picking the highest utility is also reasonable in some contexts, because fairness doesn't matter as much in that context. And then for other contexts, you might want to pick an option somewhere in between. But the main thing here is that this choice is, again, super context dependent. You sort of need to understand your application and how important fairness is, how much you can lose in utility, and then you have to make that choice. There is no correct answer. So if there's one thing that you take away from this talk, I'd say it's fairness is very contextual. There's no right way to measure it. There's no one right way to implement it. You really have to understand your problem domain and think about all these aspects to make a, to get the full picture of what fairness means in your context. And to sort of underline that, I finally wanted to talk about the role and limitations of fairness metrics. Because fairness metrics, of course, help us to formalize fairness in the context of our problem domain. They can help us spot issues with our model, but they're only a puzzle piece in the bigger piece of fairness. So if you're looking or thinking about the fairness of your data science project, there are a lot of aspects to think about. You have to think about the problem formulation, the data collection, other technical properties of your model, how you're using that model, is the usage fair towards people? And the fulfillment of fairness metrics is just a small aspect of this, but there are many other important factors when thinking about the fairness of your project. So what can companies actually do? I think it's very important to think about fairness from the very beginning to make it a key, an important factor in the design from the beginning. And it starts with the problem formulation. And then the thing that we looked at is, of course, the models and checking the models, evaluating them by using fairness metrics and seeing how well they do by picking a fairness metric that you think makes sense for your context, and having this validated through independent and external audits. Yeah, so finally, I wanted to introduce my team and the projects that we work on. So as I said in the very beginning, we're an interdisciplinary team of researchers. So we're 8 researchers based in Switzerland and Italy. My background is in computer science. Other team members come from philosophy, people and analytics. And so we use approaches from different disciplines to work on algorithmic fairness. And we have 2 bigger projects at the moment. The first one is the one that I'm part of. That's a 4-year project. The second one is a 2-year project where we collaborate with several companies, on algorithmic fairness. And the goals of our future work is to develop a methodology for making this choice between fairness metrics. And as you may have noticed, it's quite difficult to think about which metric is appropriate in what context and how to make that choice. Then we'll also look more into how we can balance different optimization goals. And finally, we're currently developing a tool and a web app, the Fairness Lab, to enable discussions between stakeholders and visualize some of these issues and trade-offs and choices that have to be made. Yeah, so thank you so much for coming to this talk, for listening. I'm really looking forward to the discussion. If you want to reach out at any point, you can just email me. And if you want to learn more about our projects, you can go to fairai.ch.